Welcome to week 7 recitation for CEE222. And let's get started with this first question, 6.1.1. So the question asks us in these 5 different situations whether the flow is steady or unsteady, and uniform or varied. So let's look at the first question. So in the A situation, the problem says that we have a constant flow in a long prismatic channel with a mild slope. So under this condition, what is the status for the flow? To do that, let's first look at the definition of the steady flow. So steady flow means that the flow rate will not change with the time. So this term will be zero at different section in the channel, as well as the depth of the flow also equal to 0 in any point in the channel. And for uniform flow, that means that the water depth will not change in different sections. So that means dy versus dx is 0. So if this is a channel and this is the flow, the y here should remain the same. That's the uniform flow. And the steady flow, that means if this is the channel, and we have a flow like this, but they are remain the same. This is y, but these are remain the same for any time, step. So these two have two different definitions, and after we acknowledge it, that's back to the problem. So because they say we have a constant flow, so that means Q is a constant. So it's already satisfied the first condition for the steady flow. So with this first term, we say that, okay, this is already a steady flow. And next, we want to examine whether it's a uniform or not. And because they say it's a long and mild slope, it's a very long and mild slope, like this. So we say the water depth is remain the same in this channel. So that means this is a uniform flow. Okay, so for the situation B, the problem says the flow in the transition of the channel in part A to a channel with a steep flow. So now we have a channel look like this. This is a mild channel from the part A and translates to a steep channel. So the flow might look like this. Okay, so if we have this picture in mind, we know that is the same channel and the same setting for the flow rate, which is the constant. So this part is still steady. However, we can see that the water depth in this channel, is changing in this transition part. So this is not a uniform flow anymore. It is a varied flow. Okay? And now let's look at the situation C. The situation C says that the flow on the sloped parking lot during a uniform intensity rainfall event how do we interpret this? So we have a parking lot. Let me clean this out a bit. Okay, now we have a parking lot, and we have a uniform rainfall event here, which uniformly drops the water onto this parking lot. So this already tells us, because this input flow is uniform, so that actually means the Q is constant in this case. So that means it is considered as the steady flow, because we have a constant input which is equal to the flow rate. But the water will gradually split out through this platform. Okay, so they will do like this part. So it is not a uniform flow, because the depth here is decreasing. Can you see the figure? So if you keep dropping, if you keep dropping the water onto a spot, the water would flow to the side, but at the same time, this part, we also have the inflow from the rain. So the flow might look like this. I exaggerated, but something like this, because the flow from the center will flow to the side, but we also have the input from the side, so the depth is changing in this case. Therefore, we say that this is a varied flow. Okay, now let's look at the situation D. The problem is the flow on the flow on the slope parking lots during a rainfall event that decreases in intensity over time. So the keyword is that the intensity is changing across over time. So that means the Q is not a constant anymore, and this tells us this is an unsteady case. And the same thing here, because we have a rainfall here, and it's a flat plate, so the flow will flow to the side, which also have the input along the path. That means the flow depth actually change in different location. So it is also a varied flow. Okay. Now let's look at the situation E. Flow in the prismatic channel from the rapid opening sluice gate. The keyword is rapid opening. So because different opening will result in different flow rate. So the flow rate is not constant in this situation with the rapid open gate. So this is an unsteady flow. But whether it's a uniform or varied flow, if we have a sluice gate, look like this, and you rapid opened it, no matter what you open, we usually have this decreasing water level in the channel. This is the datum. This is Y. So because and also this gate is opening, so the depth of the flow of the water level is also changed because of this opening gate. Therefore, it is also a varied flow. Okay, and the last one, that means write the last one if here. In the F situation, the problem say the flow during the dry season in an urban string. So the keyword here is dry season. Sorry, wrong spelling. It's a dry season. Okay. Why that is a keyword? Because that means we don't have any input for the string flow, and that's resulting that the Q, the flow rate, is a constant. And this tells us this is a steady flow. However, because we don't have any input to the channel, so the flow rate, the flow depth in the string is unlikely to maintain the same water depth, because if initially we have wait a second. If initially we have the depth like this, but because we don't have any input, so we might slowly decrease it, decreasing the water depth, but it can happen in the other way around. The point is that the water depth cannot be maintained because there's no input in the channel. So we call this also a varied flow. Okay, so now we explain the 6 different situations and to categorize them into either the steady, unsteady, or the uniform varied flow. Okay, now that's like the problem 6.2.1. So in this problem, we have this irregular shape cross-section area for the channel with the width on the top is equal to 4 meters and the width on the bottom is equal to 2 meters, and here is equal to 1.6 meters, and here on the wall on the left-hand side is equal to 3.6 meters, and it's a concrete channel, so the Manning coefficient n is equal to 0.013, and you can find this information in the table 6.2. And the problem gives us the flow rates equal to 30 cubic meters per second, and they want to access what is the slope of this channel. It's not here, so that is the things we try to solve. So in this problem, we will use the Manning equation to solve it. So let's first write down the Manning equation. That the flow rate is equal to 1 of n times the cross-section area of the channel times RH to 2/3 power and is 1/2. Okay, so this RH is the hydraulic radius, and this is a slope, which is the things that we want to solve in this case. And the area is this area, the cross-section area of this channel. So we already know the flow rates, and because we have all the information for this channel, so we can also calculate the cross-section area for this channel. And X is the things that we want to solve. The things that we need to further derive is this hydraulic radius. Okay, so let's start with the area. And we know that's 4 minus 2, so this section here is also equal to 2 meters. This section here is 3.6 minus 1.6 is also equal to 2 meters. So we have the length in here is 2 and 2 times the square root of 2. Okay, so if we want to calculate this area, we just need to calculate rectangle area here minus this small triangle. So the rectangle area is equal to 4 times 3.6 minus the triangle area here is 2 times 2 times 1/2. And this gives us that's the area is equal to 12.4 meters square. Okay, so the next things we want to calculate is this hydraulic radius. Hydraulic radius. And we know the hydraulic radius is equal to the cross-section area divided by the weighted perimeter, P. And the area we already calculate is 12.4 meters square. The weighted perimeter is 3.6 plus 2 times the square of 2, square root of 2, and plus 1.6. So let me write down. Okay, P is equal to 3.6 plus 2 times the square root of 2 plus 1.6, and this is equal to 10 meter. So that means we divide 12.4 by 10, and this will output 1.24 meter. Okay, so now we have, let me change the color. Now we have the area equal to 12.4, and this hydraulic radius equal to 1.24. And we know the Manning coefficient is equal to 0.013, and we also know the flow rate is equal to 30. So from this equation, we can solve the x. And here I just give you the answer, which the slope in this case is 0.00742. Okay, so we have the answer for these is 0.000742. Okay, so this is a relatively simple question, because if you know the main equation, you just plug in all the information that you need, that you have, and then you can calculate the only unknown, the slope. Okay, let's move on to the next one, the problem 6.2.4. So here we have a rectangular channel, look like this, which have the width equal to 3 meters. And the question gave us the flow rate is equal to 50 cubic meter per second, and the mining coefficient is equal to 0.022. The slope is equal to 0.041. And the problem wants us to solve this normal depth. We want to solve this yn. Okay, so similarly, we will start with the mining equation. So the mining equation tells us the flow rate is equal to 1 over n times the area times the hydraulic radius to the power of 2 over 3 and times the slope to the power of 1 over 2. Okay, so let's see what we have already. We have the flow rate here. We have the mining coefficient here. We also have the slope here. And the area and the hydraulic radius, they are all related to this yn that we want to solve. So that just need to express these two terms in one n, then we can solve this equation and find out what's the value for this normal depth. Okay, so let's start. To do that, you can find the corresponding equation for the area and the hydraulic radius from the table 6.1. Okay, but here I just write it for you. This is a wide rectangle channel, and if it is rectangle channel, the area is equal to b times y, which is y, and I just write down in terms of y instead of y. Okay, so this is equal to 3y, and let me still write down then. Right, and okay, this is the equation and this is a number for our specific question. And for the radius, hydraulic radius, RH, we have the equation show that is, actually you don't really need a table, you can derive that yourself, because this is area times the weighted perimeter here, and the area is equal to 3yn, and the weighted perimeter is yn plus 3 plus yn, so it is 3 plus 2yn. Okay. So now we already expressed these two terms in yn. We just plug these two terms back to this equation and plug those information back to this equation, then we can solve the flow yn. So let me write down the final equation that we will use to solve yn. So the flow rate now is equal to 50 is equal to 1 over 0.022 times the error is 3 times yn, and times the hydraulic radius is 3 yn, 3 to yn. To the power of 2/3 times times the slope 0.041. Okay, so this is final equation that we will use to solve yn, and you will need your calculation. Use solve to solve this equation. Then you can find out that the yn is equal to 2 meters. Okay, so that's a way when you don't have any other information, then you can use the equation and use the calculator to solve the yn in this way. But we have the alternative. If you use the figure 6.4a, then you can calculate least turned and least turned, and use the figure 6.4a to find out the corresponding normal depth for rectangular channel that is equal to 1.89 meter. So slightly different from the way we use the equation to solve it, but either way is fine for our case. So that's the two different methods that you can use to solve the normal water depth. But just remember, if during the quiz, most likely I will want you to solve this yn using the many method that I show here instead of the figure. Okay. Okay, so this is the last question for this week, the 6.2.8. So similarly, we have a rectangular flow channel with the width equal to 20 feet. And the problem gave us all information for the original channel with the width equal to 20 feet. But the problem asks us to solve the new normal depth if we expand the width of the original channel into 30 feet. Okay, and we have the flow rate equal to 2,520 cubic feet per second. And we want to solve this new normal depth. And just for the simplicity, I write this new flow depth, new normal flow depth to this y. So we want to solve this number. Okay, so for this kind of question, we'll always start with main equation. So let's just write down the main equation for this problem first. Flow rate equal to 1.49 divided by n and times a times the hydraulic radius to the power of 2/3 times the slope. Okay, and just remember, because we have English unit, so the coefficient, the constant here is 1.49 instead of 1 that we used in the SI unit. Okay. So in this problem, we expand the width of the channel, but the flow rate remains the same. So the idea is that we write the right-hand side part for the original problem, and that will equal to the right-hand part for the new channel. So that's the idea. We use the same flow rate as our target to solve this problem. Okay, so let's just do a small modification for this equation. We can expand this hydraulic radius into the area divided by the weighted perimeter. So if we will write that, we will have 1.49 and A to 3/5 times P to the power of -2/3 and times the slope. Okay, and because this is the rectangular channel, so we know that the area is equal to this is B times Y, and the weighted parameter is 2Y plus B. Okay, so we plug these two terms into these equations. So we will have these. No, not 8 anymore. BY 2Y plus B times slope. Okay, and because the remaining coefficient remain the same for both original channel and the new channel, as well as the slope remaining the same. So we just need to we want to organize that the term that has the y involved together for later calculation. So that just further writes this equation into this form. And by okay, so to simplify it a bit, this part is a constant that is the same for these two channels. Okay, so now we want to write this part for the original channel and the new channel. So let's just plug in the number. No, let's write down the equation first, then we plug in the number. B1 Y1 to the power of this times 2Y1 plus B1 minus 2. That will equal to the new channel. B2 Y2 Okay. And originally we have this term, the constant term here in both sides, so we can cancel them out. So I didn't write in a pink color. So we only need to care about this part in the equation. So to be clear, I just erase this constant out. Okay. And then the next step is to plug in a number, and we can calculate the information that we try to solve. So B1 is equal to 20 times the depth is equal to 15. 2 times 15 plus B1 is 20 will equal to B2 now is 30 feet times Y. This Y is the things that we want to solve. B2 is equal to 30. Okay. So now you have this equation here. Again, you will use your calculator and use the solve function to solve this Y. So here I just provide you the number. That's Y is equal to 10 feet. Here is equal to 10 feet. Okay, so we have solved this problem. But this is the proper way to solve this problem, but you might observe that it's actually because the flow rate remains the same. So that means the area of this channel should maintain a constant. So 20 times 15 is equal to 300, and because we solve this, depth is equal to 10 feet. So you can see that 30 times 10 is also 300. So that's the trick way to check whether your answer is correct or not. But this is the proper way to solve the problem. And in the future, if the Manning equation, the Manning coefficient or other things are changed in a more complex problem, then this simple trick cannot be used. So try to practice this original, not the original. Try to practice this proper way to solve this problem. Okay. And good luck for your exam.